So I will talk about complexity. This talk is quite simplified, and this is just a short overview of the wider topic called complexity. So basically what we can say is that every problem or every solvable problem can be solved by computer. But in practice it doesn't always work. So for example, there are problems which take too much time, too much memory and so on. And problem solving complexity can be measured, for example, by the time used by the program. So for example, if I execute the program, it takes 7 seconds, then we can say that this duration or the time used to solve the problem can be measured as time complexity. And the other complexity is memory complexity. So for example, if it takes too much memory, or how much memory does the program execution take. So let's see how you calculate, or what kind of different ways there are to see what's the complexity. So usually the complexity or time to execute the program depends on the input. So we can say that the larger the input is, the more time and more memory it takes. So if I have a list of 3 numbers compared to a list of 1 million numbers, then we can say that the million numbers takes more time and memory usually. Depends on the problem, of course. So for example, we have a loop for number in numbers. What happens is that it actually takes n steps to go over this list. Let's say the numbers is a list. And if there are 300 numbers, then it takes 300 steps to go over this list. So the computer has to take the first element and the second, the third, and so on. And we can say that the complexity for this statement is n. And n indicates the length of the numbers, or how many elements there are in numbers. Of course, the complexity of the code also depends on the body of this loop. So if there is complicated calculations inside this for loop, it can also increase the time and memory usage. And also what we usually say is that if there is a single statement, then the complexity for that is 1 or constant. So we can say that, for example, if we add up 2 numbers, then the complexity for that is 1. If we add 2 numbers and then on this next line multiply something, then we can say that the overall complexity is basically 2, because there is 1 step and second step. But if the statement doesn't depend on this n, or it doesn't actually depend on the input size. So for example, if I add 2 numbers, it doesn't matter whether I have 300 numbers or 2 numbers. The complexity is always the same. It's just adding 2 numbers, so the complexity is 1. And for example, if there are 10 statements inside a loop, the complexity for those is still 1. For example, I have 10 calculations. I add 2 numbers, then I multiply something, then I divide something, then I subtract, and so on. I have 10 different calculations. Although we can say that the complexity is 10, but usually we say it's still constant. It doesn't, the n doesn't affect the complexity. So we can say the complexity is still 1. But I mean, the theory behind that is a bit more complex. I will not cover it here, but I just simplify it and say that the constant complexity is always seen as 1, a complexity of 1. So for example, I have a for loop here, which also contains a for loop, and I do some calculations, print something out, and count something. A simple code. So basically I just take n numbers, multiply every number with every other number, then I print it out, and then I count how many calculations I did. So the outer loop is executed n times. So I can just write it here. So let's say we have this for loop, and let's say it's done n times. Then I have another for loop, which is also executed n times. And now I do some calculations. I times then I print something out, then I do whatever. I can do a lot of calculations here, and now I add this 1 into count variable. And what happens here? The first thing is that this line is executed n times. So if n is 10, I have to go into this loop 10 times. Then inside this, I also have a loop which is executed n times. So basically I can say that I have to use those two loops are executed n times n times. So basically n squared times. And now this one is executed for every visiting or every time this program gets into this inner loop. So we can say that if n is, let's say, 3, then we get here 9 times. 9 times we have to execute this part. Although there are different calculations here, we can say, in my example, there are 3 calculations to be done. We could say that now I have to multiply this 9 by 3 and I get the complexity of 27. Yes, the outer loop is executed n times, the inner loop is executed n times, and in the inner loop there are at least 3 statements. So this is why I multiplied it with 3 here. But, and we could say that this complexity is n times 3. But actually, if we compare or if we calculate complexity as in complexity theory, then we actually don't care about this constant part here. I mean, it does change. For example, a small n. For example, if the n is 3, then there's this value 9 compared to 27, there's a lot of difference. But if this value is large, then this multiplication by 3 doesn't affect the end result so much. So, for example, if something takes, I don't know, tens of seconds, or let's say if it takes milliseconds, and this inner part also takes milliseconds, then it might affect the end result or the end duration of this whole program. But if this loop or this more complex part takes, like, let's say, hours, then this inner part, even though it takes some milliseconds, it doesn't affect the end result so much. So usually we say that all the constant complexities can be seen as 1. So basically n times 3 is actually the same as n times n. The complexity doesn't show the actual number of statements executed. It's just like the kind of group where this problem or program belongs to. So, for example, there are certain programs which are n log n, then there are n square programs and so on. So basically the main idea is to get like the big picture, or what's the big complexity for this problem. But yes, as I pointed out, this is a simplified overview of complexity. There are actually more into it, and this will probably be covered in different courses if you want to take those. But for us, it's just some information about how programs work and how we can measure the simplified complexity, or how we can compare different data structures. And now in terms of complexity and efficiency, we can say that different data structures have different efficiency. So, for example, if you want to do some operations with lists compared to doing the same things with sets and dictionaries and so on. And for example, if you want to find an element in a sequence, for example, in a list or string or set, then we have to see how it works. So, for example, for list, every element has to be considered. So we visit every element. So for example, I have 200 elements in data, and I check whether 3 is inside my data. Then I have to go over the first element, the second, the third, and so on. Of course, we can say that if the value I'm looking for is the first element, then I only have to visit one element, which is true. But in the worst case, I have to visit every element. And even if there's no value I'm looking for, then I have to still visit every element from the data. In set, it works so that elements are hashed, and basically it uses a more complex kind of mechanism behind it. And what happens is that only one element is visited. So if I have a set of 200 elements and I want to know whether Ago is inside my names set, the complexity of this operation is 1. I mean, there are cases when it can be more, but we can consider it as 1. And in dictionary, when we search for a key, this also is basically 1 operation. So in terms, if you want to find something from a sequence of elements, then it's wise to use sets or a dictionary for that. But then you have to also know that in a set, for example, you cannot use duplicate elements. For example, if you have to have duplicate names, then you have to come up with a different data structure or how to structure your program. But yes, if you know that you have to look for a certain value and you have a lot of data, then it's wise to use set for that, not list. And here's also one page where we have different data structures, and it's basically what it does is that it points out different operations and what's the complexity for those operations. So for example, there is a list, and we were looking also this X in S. So for example, I'm looking for certain value inside my list. Then the complexity is O(n). So O is just a notation to point or show the complexity. The N inside it shows the actual complexity. So basically I have to look through every element. N usually indicates the size of the input. And if I go here and take, for example, set and see that X in S, the average case is O(1). So basically the complexity is 1. Of course, there is a worst case scenario where all the elements have the same hash and so on. Then you will end up still looking through every element. But usually we can say that average case is what we can go with. And in dictionary also, if I see the key in dictionary, I can see that the average complexity is 1 here. So let's summarize what we saw about data structures. So it's very important to use the right data structure for the problem. So for example, if you know what's the task and you have some experience with data structures, you can choose the right data structure for this problem. So, and you have to also consider the functionality. For example, if we want to use something where we can append elements or add new elements, then we can say that tuple is not the way to go because tuple doesn't allow adding elements. For example, if we want to have duplicate elements inside our sequence, then we cannot use set because set doesn't allow duplicate elements. Vice versa, if we want to have only unique elements, then the set is a way to go, and so on. So in addition to functionality, we should also consider complexity. So we saw that different data structures have different complexity for different operations. If we want to look for a certain element inside our sequence, then it's wise to use something where the looking or this functionality takes less time or the complexity is lower. For example, set or dictionary. There are actually, of course, different examples where, for example, list is better or even has less complexity than, for example, set and so on. But yeah, you have to consider the functionality and you have to consider the complexity. And based on those two, or maybe even other inputs or other variables, you might want to choose a data structure for your task. So for example, if we are looking for an element, then set or dictionary is a way to go. For example, in set you can just have elements, but in dictionary you can also have mappings to those elements. But actually keys in dictionary are quite the same as elements in set. So often you can even use dictionary keys as a set. But of course, if you don't need the mapping, then maybe set is an easier way to go. And for example, if the order is important, then you probably have to use list or tuple. So, and if both are important, then you have to combine and see whether you can come up with a solution. For example, you can store order in a list just for the case you need the order, then you can go over this list and then take the elements. But you can also store the same values or yes, the same elements in a set when you want to check whether you have this element or not, or use a dictionary for that and so on. So yeah, but the basic idea is that you understand that different data structures act differently. They have different complexity. And if you are looking for an element inside a list, for example, then you should know that it's actually quite slow. This operation is quite slow. And to make it more efficient, then you probably have to use set or dictionary or some other data structure. So know what you want to do and know how the data structures you are using, how they perform.